Hello everyone, this is Ahmed Momeni and this is my presentation for the final project of the course Predictive Data Analytics in New Mexico Tech. This research is a new method, the name is Perm pair, Android malware detection using permission pairs, which uh, develop a method to find malwares. I will talk about in detail. This research is a joint research between the Technical University of Delhi and also University of Washington. This, this is a work of Anshul Arora, Sateesh Peddoju, and Mauro Conti, published in 2019 in IEEE Transaction of Information Forensics and Security. In this presentation, firstly, I have an introduction about what is Android malwares, what are the previous works, and what are the problems with permissions we have, what are the permissions. I talk about the methodology used here to detect malwares in the Android system. Finally, I show the result of this method, this proposed method, and at the end we have a conclusion and talking about the future works we can do about this methodology. In these days, there are smartphones the popular between the peoples and present several apps, do services like social networking, online banking, or online gaming, location-based services, or other conventional services like messaging and communication using that. Between the old smartphones, the researchers show that about 80% of these smartphones use Android as the operating system. As I mentioned, there are several services using software, but we have some malwares doing some tasks we are not supposed to. But what is malware? Malware is a collective name for a number of malicious software variants, including some viruses or ransomware or spyware. Shortened for malicious software, malware typically consists of code developed by cyber attackers designed to cause extensive damage to the data and systems or gain unauthorized access to a network. The evidences show that the Android are the major target for the malwares. For example, we have in 2017 we have 3.5 million malicious samples and expected to rise more and about 25 million in 2020. But what is the source of this malware? We know that the increase in number of Android malware attacks is mainly from three major sources. First, the app market, an easy distribution gateway for malware developers or users which derive downloads in several resources. For example, they can download a malware in a website or anywhere. Or developers, when use the weak code, can develop malwares and other cyber attackers use that malware. In the Android operating system, we have permissions. The design of Android platform secured by the system that use restricting the permission. They are the accessing to local resources by application. A user can see the list of permissions during the installation of an application. The list or supposed to alert the user about the resources, but most of the user ignore them and do not think about that why this application needs this permission. You can here see an example of app permission. When you install the software, you literally give this access to other uh, software, or for example, they give you give the application to access to location, to your microphone or other things. So the list of contacts, for example, and this is what most of the users do not uh, hesitate about accepting these permissions. And this point is an internal, intrinsic feebleness for the Android systems. Now let's talk about the previous methods are developed to detect Android malware. Basically, before explanation about that, I should say that every Android application consists of a file which is Android manifest and show the permissions and the parameters required by this application. Let's go to the methods. The previous methods are developed. They are broadly categorized into three types. First, static, second, dynamic, and third, hybrid detection. Then let's start with the static detection. Static solution aims to analyze the app's manifest files. Then we are talking about the component in the manifest. For example, Java code or sequences of API calls in this code. This related words can divide it to uh, other categories. So, for example, permission analysis or permission-based malware detection or permission pattern analysis or manifest file-based detection or permission graph analysis and API calls based detection. Here you can see a table which show that some uh, features that these methods use that for example the permissions, MP for permissions, or manifest file component, or virus total or genome. There being you can see the sources of these malwares, the applications we use that. I will talk about the sources we use in this research, but the features we use in the static mobile malware detection models are PMPs for the permissions, M is for manifest files, and we have API, and we here we compare the proposed method with the previous existing models. The next type of the malware detection models are dynamic detection. In the dynamic detection solution, we intend to analyze the runtime behavior of the application. The related works in this field, we have two type of dynamic detection. We have operation system level detection or network level detection. In this table, as you can see, you can see the features that this model uses. We have the DL show the dynamic logs of this application or the system events. Here we have the SE or KL, which is the kernel logs or the system calls, and also we have the traffic used by uh, the software, or also we have the permissions that these proposed methods use that. We have also the sources this application use that, and you can see we have a comparison between the previous works and proposed works. The next type of the methods is models, hybrid detection models. Hybrid detection models aim to combine do two previous uh, methods, statics and dynamic component, to detect malware. Uh, we have also another table here shows the previous works that this model use the features like system calls, app components, manifest file, or static APIs or dynamic APIs, and permissions. You can see the source of this software also here. Then the next step, let's talk about the methodology we use in this research. This research analyzed the permission as a subset of group of all permission have the software have, but to uh, reduce the complexity of systems, this paper just use permission pairs, which means subsets of the permissions with just two members. In order to do the analysis on permission pairs, there are they have some samples, malware samples from different sources. The sources here is the genome, the RIN, Kudus, and besides that, there are some downloaded normal Android apps from Google Play Store. Then we have genome as the sources of data sets. We have genome, Derwent, and Kudus for malwares, and for normal software we have the data from Google Play. The proposed model consists of three phases as shown in this figure. The first phase is graph construction phase, which extracts the permission pairs from each application to form a graph. Four different permission pair graphs are here: genome graphs, driving graph, and Kudus graph. And we have a normal graph. They are built from this phase, the first phase. Typically, every new dataset used in this analysis and detection needs to construct the graph. The next step, the second step, is graph merge phase. With the merging of all malicious graphs into a single malicious graph, we have a model of malicious software. At the final step consists of two graphs, a normal graph and a malicious graph. Then subsequent phase propose a detection algorithm to distinguish normal and malicious apps. The model at the last, which should eliminate the irrelevant edges that not affect the detection result. As I mentioned, the first step is graph construction algorithm. This proposed model uses a graph to represent the relationship between the various permissions in each application. This model applies to a graph that we showed here with G uh, to have two parameters V and E, representing that the V is the vertex of the graph and E, which are the weighted edges between these vertex, shows the pair of permission connected. Each edge weight increase with the occurrence of the same permission pair from different application. Then an application with single or no permission does no contribution to any analysis here. The algorithm is extract the permission from each application and generate all permission pairs. If an application has n number of unique permission, then we have the uh, selection of two in n group. For example, if we have an application with three permission, we have three different weights. Once we after we process all of the apps in datasets, we divide all the edge weights to the total number of apps in the dataset to normalize the weight. The next step is merging the previous graphs together. If you remember that we have the three different graphs from genome, from driving, and from photos. And by doing some algorithm, we normalize the weight and make a unified graph. And in this merging, we have two types of edges. One are common edges and disjoint edges. We insert all of the disjoint edges along with their edge weights and consider common edges, which is the summation of the weights of three different graphs. The last step in this research is detection and discerning between the normal and malicious software. In this step, for every testing app, the algorithm extracts its permission pairs with the first step, and the procedure uses two scores, normal score and malicious score, for testing the app. This score can be calculated by searching every permission pair of the testing app in both the GM, which is the graph for malicious software, and GN, which is the graph for normal softwares, and adding the corresponding weights. If malicious score is greater than the normal score, then the procedure declares that the app is malicious. This technique is based on the fact that higher the weight of the permission pair in a malicious graph means higher is the chance of any app containing that permission pair to be malicious. Then if we go back to the previous slide, as you can see here, we have some graphs from the data sets. We know that they are malwares, and we create from the tested app that which graph does have. Then we uh, compare these two graphs with the normal graph or malicious graph by checking the weight. And if the score for this test app, uh, the malicious score is more than the normal scores, then we found that uh, this is a malware. Here you can see a test from the Darwin graph. We use the Darwin dataset, and as you can see here, we have the scores for the top 10 permission pairs. In this graph, you can see, for example, if we have a pair of internet and RPS permission, then or other pairs, then our software prone to be a malware. In this table, we have a comparison between the proposed graph we use from different datasets. As you can see, if we use the genome graph, uh, or we have a better result as a Darwin graph. And if you look at the overall accuracy of this detection method, we can see an overall accuracy more than the 95 use the merged graph. At the end, let's have a comparison between the proposed method with the previous methods already used. We can see that the number of malicious apps detected by the several methods using test dataset, and you can see that we have very good result using the Perm pair. Then as a conclusion, as a brief conclusion, I can say that using the pair of permissions and comparison with the basic graphs, we can have a cost-efficient method with a good accuracy.